Hey, everyone. I'm Rob Zellem. I'm a scientist at NASA's Goddard Space Flight Center. I'm an exoplanet scientist, and my official role is I am the communications scientist for the Nancy Grace Roman Space Telescope. And I'm also the project lead for Exoplanet Watch, a citizen science project to observe transiting exoplanets. So my background is exoplanets, and I'm going to talk about finding life in the galaxy because I am a giant nerd. So if I talk too quickly or if I use some terms that you cannot, I haven't defined, feel free to interrupt me or wave your hands up in the air to interrupt me. And I am happy to take a second and explain those as well. All right. So you're all here at your high school tonight, and you're learning about these Galaxy of Horror posters. They're really amazing. They're made by the Jet Propulsion Laboratory out in California, just outside of Los Angeles. They have these really cool posters about this roasted planet, HD 80606b, this other planet that has rain, basically like glass shards in its raining down called HD 189733b. Dark energy as well, which is something that we know that's out there, but we have no idea what's causing it. And then dark matter, this unobservable matter out there that is causing galaxies to spin more quickly than they should. So we have all these really cool things highlighted with these posters, and it's really interesting to have the public start getting excited about these various. So really fortunate to have those and have a really great working partnership with JPL. So I'll be talking about these cosmic posters tonight and sort of tying them into my talk. But one quick thing about myself is when I tell people that I'm an astronomer, people usually ask me if I ever wanted to be an astronaut. So right here is me when I was a little kid at Kennedy Space Center outside of Orlando. If y'all haven't been up there yet, it's a really great trip. It's really cool to see KSC. And I'm meeting my hero, the astronaut here. Um, Unfortunately, though, I'm very scared of heights, so I am what I think is the next best thing, which is an exoplanet astronomer. And those in the astronomy club that are in the audience today, a little patience here while I explain what this means. Exoplanet, that's just short for extrasolar planet, where extrasolar means anything outside or beyond our own solar system. Planet, hopefully you all know what that is. If not, talk to the Astro Club folks in the room there. So exoplanet is any planet outside of our own solar system. And I'm an astronomer. You probably all know what that is. That's someone who stares at the sky or more likely their computer for way too long. I actually don't do a lot of observing. I probably observe remotely these days at telescopes maybe once or twice a year. Most of my workday is spent on my computer in meetings or talking to students or doing my own research and coding. We do use telescopes a lot, but a lot of the data now these days is robotic and automated, which is really nice because I can be in my pajamas all day as opposed to having to go out to the telescope. But I still do like to go to observatories just to make sure I have that sort of connection with, where folks have been observing with the past few hundred years. So, as an exoplanet astronomer at Goddard and at NASA, what I'm trying to do ultimately is answer that ultimate question of are we alone in the universe? Like I mentioned before, giant nerd, I love Star Wars, and I want to ride the Millennium Falcon. In order to do that, we have to know where it is docked. And that's what's one of the many nerdy things that are inspiring me to become an astronomer and to answer this age-old question. So even though exoplanets is one of the newest fields of astronomy, it's only really been around since the mid 90s. It's an idea that's been around for hundreds, if not thousands of years. So for example, Giordano Bruno, he was a 16th century philosopher. He's this Emperor Palpatine looking dude here at the top right. He postulated that there are other worlds outside of our own solar system and potentially they could contain life. Isaac Newton, this guy that discovered fig Newtons, also discovered the theory of gravity, said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, we have 8 planets in our own solar system. And if we go out into the night sky and we look at all those stars up in there in the sky, it stands to reason that those stars also have planets around them as well. And now we know a few hundreds of years later that these two guys are absolutely correct, that there are at least as many planets as there are stars in the sky. And as we get better technology, as we know where, when, and how to look, we're discovering more and more planets every single year. So in the mid 90s, and even the early 2000s, planet discovery was something that was really impactful and incredible and exciting. Now it's honestly kind of more passé because we've discovered so many planets. Upcoming missions, such as TESS, which has been flying for the last few years, that's expected to discover an extra 10,000 planets. And then the Roman Space Telescope that I work on at Goddard, that's expected to discover hundreds or tens, if not hundreds of thousands of planets. So we're really in the golden age of exoplanet discovery and also characterization. So again, what I'm really interested in personally is searching for life. And we can sort of boil it down into this three-step method. First, we have to find an exoplanet. We have to find the rocks, the gaseous bodies that we want to study. Then we actually have to determine if that planet could support life. But just because it could support life doesn't guarantee that it has life on its surface. So then we have to go to step three, which is actually find if life exists on the surface of that planet. So let's first look at the variety of different methods that we can use to find exoplanets. Well, unfortunately, this is actually a really difficult thing to do because it's really hard to see exoplanets because they're so far away. We typically only see the star that's orbiting. That's just simply because the star is so much brighter than the planet. So we need to do one of two things. We either need to use indirect methods to infer that a planet is there, or we need to block out the star's light so we can see the planet orbiting around that star. So we actually know of a variety of different ways to find exoplanets today. But the ones that I'll be focusing on this afternoon slash evening are the radial velocity, the transit, the direct imaging, and the gravitational microlensing methods. The radial velocity and the transit method have arguably given us the most understanding and the most knowledge that we have about exoplanets to date. The direct imaging technique is extremely exciting, in my opinion, because this is where the next generation of exoplanet characterization and discovery is going, including the search for a potential Earth-like planet. Then lastly, gravitational microlensing is extremely interesting because it enables us to look for planets that are very similar to those in our own solar system. Because right now we're mostly looking at big planets close to their star that are definitely not habitable. All right, let's look quickly at the radial velocity technique. This is sometimes called the Doppler shift or the wobble method. So when you have a planet orbiting around a star, the planet stays in orbit around its star due to the star's gravitational tug on its planet. But the planet has its own gravity. So as the planet orbits around the planet also tugs the star back and forth. So the planet actually induces a wobble of the host star itself. So the star looks like it's coming towards us and away from us. And if we can observe that wobble over time, we can actually infer that there's a planet orbiting around that star. In addition, we can also measure the size of the planet, the mass of the planet relative to its host star. The bigger the planet, the more gravitational tug that induces on its host star is a lot greater. So it's a really, really powerful method for effectively weighing planets. The other method is the transit method. So if we're really lucky and we're observing a host star, sometimes that star will have an exoplanet around it. If we're even luckier, the geometry will be just right so that the planet will appear to pass in front of the host star, blocking out a portion of the star's light and causing the star to appear to dim. And this method is extremely powerful because this tells us how big the planet is, its radius, its area is compared to the host star. The bigger the planet, the larger the dip in brightness that the planet will block out. Smaller the planet, smaller the block in brightness of the host star. And as I'll be talking about a little bit later, this method is also extremely powerful because it enables us to study the atmosphere of the planet itself. Because when the planet passes in front of the star, not only is the optically thick disk, like the rocky portion, for example, of a planet blocking out the star's light, but also the very thin annulus of atmosphere absorbs some of the host star's light as well. And this method has been used very, very successfully to discover about 4,000 of the currently known 5,000 exoplanets to date. So the transit method has given us the most planets in terms of discovery space that we've had to date. Some advantages of this method, it's actually really relatively cheap to do this. I saw online a few years ago, someone took a regular DSLR camera, put it on a very simple tracking mechanism, and they were able to observe an exoplanet just using a camera alone. And again, this determines the planet's size. Some disadvantages, though, is that we're biased towards large planets. The bigger the planet, the more light it blocks out, the bigger the signal, the easier it is to see them. And also in short period orbits. If a planet orbits around its sun every 5 days, then that's only 5 days we have to wait in between transit events when the planet passes in front of the star. But if I wanted to look at an Earth-like planet, that signal is 100 times smaller than that of a Jupiter-sized planet. And I have to wait once every 365 days to see a transit of an Earth-like planet. But as I mentioned before, a lot of these planets are being discovered right now with a mission called TESS. This is NASA's Transiting Exoplanet Survey Satellite. What this mission is doing is it's slewing around the entire sky to observe and sample the entire sky to look for new transiting exoplanets. So right here is a picture of TESS with its solar panels, its high gain antenna to transmit data back to Earth. And on board, it has these four little digital cameras that allow it to take like an image, a slice of the sky. And over the course of a year, TESS will sample and slew across the entire northern hemisphere about the course of a year. Then the next year, it goes down to the southern hemisphere, and it sort of flips back and forth year to year. And then TESS will be doing potentially other surveys as well. But TESS, again, is predicted to discover up to 10,000 new transiting exoplanets, in addition to the 5,000 that we have today. So TESS alone will potentially triple the number of known exoplanets to date. So you might be wondering why we care about observing and discovering more and more planets. One reason is demographics, because we need to have a statistically sound number of planets to do statistical surveys of these planets to figure out how common Earth-like planets or Jupiter-like planets are. But also, we need to find the best targets to follow up with space-based telescopes. Space-based telescopes such as Hubble, the James Webb Space Telescope, the Ariel telescope, which will be launching at the end of this decade. It's a European Space Agency mission. Even next generation telescopes that'll be launching in the 2030s or 2040s will likely be using the transit method to observe and characterize exoplanet atmospheres. And we want to ensure that we have the best targets so we don't waste time on these telescopes. Hubble and James Webb, for example, are oversubscribed by a factor of 10 to 1. So for every 10 proposals, only one of them is accepted by NASA to go on those observing runs. So we really need to use them as efficiently as possible to ensure that they work as efficiently as possible, to ensure that they're able to achieve as much science as possible. One other part of that is that we have to really keep things fresh. So if I want to observe a specific exoplanet like HD 189733b, which has that glass rain on in its atmosphere, or HD 80606b, which is that planet that has very intense heat and then very intense cold as it gets farther away from its host star, we have to know very precisely when those transits would occur. Typically, what we've done in the past is if there's a 5, 10, 15-minute uncertainty in that next transit event, we just bake in an extra 15 minutes of time. But again, these resources are extremely precious, and we want to use them as efficiently as possible. So what we can actually do is get folks such as yourselves to help us to observe transiting exoplanets. So on the right is actually a sample data set of a transit taken from a small 6-inch telescope out in Tucson, Arizona. And right here, you can see the host star, and then the planet passes in front of the star, blocks out the star's light, causes the star to appear to dim, and the planet gets back out of the way, and the star gets brighter again. And from this, we can actually measure very precisely using a single 6-inch robotic telescope out in Tucson. We can very efficiently measure and very precisely measure the mid-transit time or the timing of when these transit events occur. And we can use this data to then help out inform or predict when the next transit will occur with missions like James Webb. And that's exactly what we're doing on Exoplanet Watch, which is our citizen science effort to monitor transiting exoplanets. So folks like yourselves can help us analyze a bunch of historic data, or if you're lucky enough to have your own telescope, you can do your own observations yourself, and you can help enable NASA science. We're a collaborative effort to complement existing surveys. All of our data is immediately public. If you go to our website right now, you can download any of our observations and any of our data products. You can actually write your own papers. We've actually had high school students involved, and actually some folks even in middle school as well involved in our project. And we've had some high school students writing their own first author papers where they'll pick a planet and they'll study it in detail and become a published author even before they even go to undergrad, which is pretty incredible. Um, we have target requests by professional astronomers. All of our observers are listed as co-authors if the data has not been previously published. If you do the work, you deserve the credit. And we're funded by the next few years by NASA's Universal Learning, so we're directly funded by NASA, which is pretty exciting. So as a citizen science project, we have two goals. We have our educational goals and our science goals. I kind of talked about the science goals before, which is to really, at its core, is to help update the timing of these transits. But also, we're really trying to help engage and teach the public about exoplanets and enable them to do science, and hopefully, ultimately, to inspire folks to become an astronomer, professional astronomer at the end of the day as well. So here's a quick roadmap of our entire user experience. It's a little overwhelming. I'm going to step through it right now. So let's say you have your own telescope. What you can do is go on our website and you can use our built-in planning tool to help figure out what you should be observing tonight in your own neck of the woods. And then you use your own telescope and observe. I used to live in Southern California, so I do not have lots of liquid income. So what I do instead is I do not have my own telescope. I request data from our own database. We are very, very fortunate that the Micro Observatory, here's one of the photos of them right now. This is this collection of 6-inch telescopes out in Tucson. They've donated over 11 years of data to us, hundreds, if not thousands of data sets. And we need your help to help us to go through all these data sets, analyze them, reduce them, and then contribute them to our project. So you can go on our website right now. You can type in your email address, and within a few minutes, you'll have a unique data set sent to you. And you can request data right now every 2 days. After you get the data, you can analyze it using whatever analysis code you want. Lots of people use many different code sets. We have our own exotic that we've actually specifically built so it can run on a smartphone. So if you have a smartphone or a Chromebook, you can totally participate in this project. What's really great about our code is it runs completely in the Google Colab cloud. So you don't need to download anything. You don't need to install anything. Just follow our tutorials. We have both written and video tutorials as well. And we also have a very active and friendly Slack channel. So if you run into any issues, you can get in touch with us that way as well. I'll talk more about Exotic in a second. But after you analyze your data, you upload it to our online database. Then you sit back and relax and you hopefully get your data published. Or you go into our results page right now and analyze whatever data you want. And you publish it yourself. You just ask again, you give the astronomers who did the observations credits, you give us an acknowledgement, and you cite our paper. Exotic, it's a little text heavy, sorry about that. This is our Google Colab code. So this runs completely in the cloud. You don't have to install anything, and I've run it on my smartphone before as well. This is actually the literal same exact code that I use professionally as an exoplanet astronomer. What this does is it takes those image files that you've taken on your telescope or from the Micro Observatory, for example, and it fully runs the entire analysis with your help and guidance. And then it produces this light curve at the end of the day, this measurement of the exoplanet. So in just a few minutes, usually about 5 to 10 minutes, you can go from getting data from us to producing a data set where you can actually measure an exoplanet casting a shadow all the way down here to the Earth. Really, the only difference between exotic on how the public use it and our user uses it is just the interface. It's just a bit more friendly user for interface that folks can use than what I'm used to myself. We've also had this big December 2020 observing campaign where we actually helped the James Webb Space Telescope save about 4 hours of time, which is roughly worth, last time I checked, a few tens of thousands of dollars. Basically, if you take the expected lifetime of James Webb and divide it by its cost, that's how you can figure out how much the time saved was worth. This is actually of HD 80606b. So it's actually this exoplanet, the roasted planet that you might have seen out at the exhibit tonight. But this exoplanet is extremely interesting because it has a very long orbital period. It gets very close to its star, and then 100 days later, it gets very far from its host star. So it experiences extreme weather changes. But since it has such a long orbit, it takes about 12 hours for it to transit the disk of its host star. So a single transit event right here takes about 12 hours. With a transit observation, we also need to get out of transit baseline, data before and after the transit itself. So we're looking at over 12 hours of data taking. And this is literally impossible for any single user across the globe to do. So what we've done here is I think we're the first group to ever do this worldwide, was to simulate a single globe spanning telescope. We had our users out here in Eastern Asia start to observe. Then they passed it off to folks in India, right here. Then they passed it off to folks in Eastern Europe, the Canary Islands, down to the west coast of the US. And this person in blue observed it the first night and also the second night. And we stitched all this data together to patch together this single light curve, this single observation. What was really cool as well is we had 24 facilities participating in this project. All of them were telescopes under about 2.5 feet big, so relatively small telescopes. A lot of them were telescopes only about 3.5 inches big, so relatively small apertures. We probably had another 20 to 40 people that wanted to participate in this campaign as well, but of course, the night was extremely clouded over throughout the Northern Hemisphere. We had a ton of users in Western Europe that were clouded out. The entire East Coast was clouded out. So this shows the power, the potential of having this vast user network. We can observe longer transiting exoplanets, but we can also help guard against clouds. Because while it might be cloudy in Texas, it might not be cloudy in Southern California, for example. So we can sort of hedge our bets and spread our pool kind of wide. And again, that was all in support of this mission of this exoplanet. And we've saved about 4 hours of James Webb time thanks to this effort. So if you're interested in getting involved in Exoplanet Watch, our citizen science project, you can scan this QR code. You can also just Google NASA Exoplanet Watch, and that should be the first thing that pops up. There are other amazing citizen science opportunities as well. I believe the website is citizenscience.gov, from everything about astronomy to even looking at clouds, aurora, bugs, anything dealing with nature. You can definitely help out. And scientists like myself need your help to help us do the observations. There's another citizen science project about exoplanets called Planet Hunters TESS. That's Planet Hunters TESS. We can actually help the TESS spacecraft I talked about a few slides ago help us discover planets that the TESS scientists might have missed. So you can actually help us discover new exoplanets as well. All right, that's sort of my side track on sort of pitching for Exoplanet Watch there. Now let's move on to direct imaging. So direct imaging, as you've probably figured out, is taking direct photographs of exoplanets. Astronomers are not very inventive people, unfortunately, when it comes to naming conventions. But as I mentioned before, this is really hard to do. because it's really difficult to see the glint from the planet or the light from the planet through the light of the star. If we take a really big planet that's just recently formed, so it's still hot, it's still radiating heat, and we put that around a sun-like star, that planet is still a million times fainter than its host star. That's like looking for the light of a firefly around a lighthouse, and that lighthouse is off the coast of Seattle. And you're observing it from Miami. Those planets are all well and good. What I really want to do is help find an Earth-like planet. So if we take that same Earth-like planet and put it around our sun-like star, that planet is 10 billion times fainter than that star. That's like looking for one bioluminescent alga around that lighthouse off the coast of Seattle. So the question is, how do we block out the light of the star to observe the planet orbiting around it? Some of you might have been lucky enough to see the total solar eclipse. And during the eclipse, the moon passed in front of the sun. It blocked out the sun's light, and you can see the outer layers of the sun called the corona. You could also see nearby stars to the sun as well. Astronomers realized the scientific impactfulness of observing eclipses. So what they were able to do is they invented something called a chronograph. This is a disk that passes in front of the sun, blocks out the sun's light, and enabled them to study the outer layers of the sun. Now, 100 years later today, we're using the same technology, more or less, to block out far away stars so that we can see the planets orbiting around them. So right here, this is actually a really nice video. Let me share my stereo sound right here. Oh, if I can. Oh, I can't. Never mind. I will talk through this video instead. So this is a really helpful video on how astronomers can observe exoplanets. So this is with respect to the Nancy Grace Roman Space Telescope and its chronograph instrument. What it's able to do is it takes in the light of a star system and it's able to move a chronograph disk in front of the star to block out the star's light so we can observe the planet orbiting around it. In the instrument itself, we have this little disk to block out the star's light. We have this secondary donut to further mask out any light that's bent around that inner disk. And from that, we get this little image of a bunch of noise, but mostly the stellar signal is blocked out. From there, we can actually activate our deformable mirrors here, very thin mirrors with tons of pistons behind them that can further amplify and correct the signal. And then we can use advanced post-processing software to then further bring out the signal of the planet. So what's really exciting about this method is we can actually take photographs of the planets orbiting around their host star. And this technique has been used very, very successfully from the ground. So here's actually some data taken from the Gemini telescope over about 7 years. Right here at the center of the image is the host star blocked out by the chronograph disk. Now, chronography isn't perfect. Some of the star's light does diffract and bend around the disk of the chronograph. You see those little speckles. But if you see these four little points of light, these are actually four exoplanets orbiting around their star in real time for about 7 years. So they're actually able to make movies of extrasolar solar systems. So the other method that we use a lot to find exoplanets I'll be talking about today is the gravitational microlensing method. And this is one of the hardest to sort of explain as well, so bear with me. So as you might be aware of is that matter is able to bend space-time. And as a result, light can be bent by things that are very massive like the sun. So for example, if we're looking at a distant star in the back of our universe, if we're very lucky, there might be something that passes in the foreground in front between us, the Earth, and that background star. So there might be a star that passes between us and the background star. And what that foreground star does is it focuses the light here on Earth. So it acts sort of like a magnifying lens. So that background star suddenly will get brighter in its over time. If we're even luckier, that host star in the foreground will have a planet around it. And the planet as well will help amplify or focus the light here on the Earth, and we'll get a secondary little increase in brightness. So with the microlensing technique, we can look for these additional exoplanetary systems just by chance. This method is extremely important because this enables us to look for planets that are much more akin to ours in our own solar system. With transiting planets, we're mostly finding big planets that are close to their star. With direct imaging, we're looking mostly at planets that are far away from their host star. So this sort of fills the gap between those two methods. And while microlensing events are super rare, the Roman Space Telescope that I'll be talking about in a minute has a ginormous field of view that enables us to observe hundreds of thousands of stars, so that even if something has a 1% chance of happening, we'll still observe thousands of them happening any given night. All right, so now what? We have discovered over 5,000 exoplanets. That's all well and good. Planet discovery is kind of getting, kind of boring in the sense of exoplanet science. But so how do we take that next step from exoplanet detection and discovery to planet characterization? How do we determine if a planet has an atmosphere? If a planet does have an atmosphere, for example, what molecules are present? Does it have methane, carbon dioxide, water? Does it have the molecules, for example, that life needs to survive? And if it does, could that planet actually support life? But then we have to take the next step and prove definitively if that planet has life or not on its surface. So now we move on to determining if a planet can support life. So when scientists sort of look at a first crack to determine if a planet can support life, they talk a lot about what's called the habitable zone. And this is the zone where liquid water could survive on a planet's surface. And the reason we care so much about liquid water is because life, as far as we know it, requires liquid water to survive. So if you look top down on our own solar system, Mercury and Venus are too close to the sun. They're too hot and water boils off. Mars is too far away, it just freezes out. Earth, however, is not too close. It's not too far. It's just the right temperature, like the Goldilocks zone, where water can survive on its surface. So it's just right for life to form. That's all well and good as well. This sort of gives us an estimate or a way to sort of determine of those 5,000 planets, which ones should we be focusing on with our time on our telescopes. And this is where we can actually use something called Beer's Law to help us characterize what these planets are made out of. So right here, this is kind of a quick little example that I drew up. If we're looking at, for example, a light bulb, and we put that light bulb behind maybe like a box full of water vapor or steam, for example. If you look on the other side of that box, you would expect that light bulb to look a little bit dimmer because the water vapor in that box of gas is attenuating or absorbing and scattering some of that light from that light bulb. If we compare how the light bulb should look, it should look bright, and compare it to how it does look, looks dim, we can actually use this equation right here to back out what is in that box that's full of water vapor, for example. So if we're looking at a yellow star, as astronomers, we expect that yellow star to look yellow. We put between us and that yellow star a giant gas and disk cloud, like a nebula. That nebula will absorb some of the star's yellow light and cause the star to appear to look red. So if we observe what the object does look like, this star looks red. Compare it to what it should look like, the star should look yellow. We're able to then use Beer's law to back out what this gas cloud is full of, that it has molecules like hydrogen and helium. We could do the same thing for exoplanets. If we look at an exoplanet, and maybe it has a bright core that's very, very hot, like Jupiter and Saturn, even the Earth. As those hot cores radiate heat away, they pass through the outer layers of the planet's atmosphere and surface that are relatively cooler, so that bright, hot heat cools down. And what was once bright and yellow is now comparatively cooler and red. So astronomers at the other side of those telescopes can actually use Beer's law to figure out if there's methane in the atmospheres of those planets. Similarly, we can look at Jupiter, for example, in our own solar system. Due to clouds in Jupiter's atmosphere, the sun's yellow light hits Jupiter's upper atmosphere, and then Jupiter reflects that light back as red light. So astronomers on the other side of those scopes can then determine that there's clouds in those atmospheres as well. So Beer's law is extremely powerful and enables us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. So we can actually figure out what these things are made out of without even having to travel there. So right here is an example data set that we're looking at of a bunch of different exoplanets. We've taken their light and we've spread them out over a variety of wavelengths. We've passed this light through a prism, and out comes a rainbow of light. And we have about 7 exoplanets here. They're arranged from relatively cool at the bottom to comparatively hot at the top, and their light is spread out a variety of different wavelengths. At these wavelengths, water most strongly absorbs and emits light. So if I see a bump and wiggle at these wavelengths, I can infer that there's water in the atmosphere of that exoplanet. Similarly, if I see a bump and wiggle at these wavelengths, that means that there's methane in their atmospheres. Or right here, carbon monoxide is in their atmospheres. So simply by looking at the spectra of these exoplanets and by using Beer's law, we can infer that these molecules exist in the atmospheres of these planets. You might have noticed these gaps in the data as well. This is because these data were taken from the Gemini telescope, which is on the Earth. One of them is on Mauna Kea. And that's where our own Earth is getting in the way. Unfortunately, the Earth has many molecules that we also want to look at on exoplanets as well. So it's like looking through between the gaps of a picket fence, for example. So if we have difficulty looking through the Earth's atmosphere at these wavelengths, what do? This is why going into space is so necessary. Again, because the Earth's atmosphere gets in the way on wavelengths that we want to study for molecules we want to study, like water, for example. This is why it's necessary for us to launch out into space. So the Hubble Space Telescope is one of the many reasons why the Hubble Space Telescope has been so extremely important to use in the field. It enables us to gain access to wavelengths that we just simply cannot from the ground. In a similar vein, the James Webb Space Telescope is doing such impactful observations of exoplanets. It seems like almost every single observation that James Webb makes is just completely changing the entire field of exoplanets. It's absolutely crazy. James Webb is predicted to study perhaps even a few hundred of exoplanets. Hubble's observed about 60 of them. James Webb is observing one, seems like every few days. It's absolutely incredible. James Webb is sort of the successor to Hubble. Hubble is about 2.4 meters across. James Webb is about 6.5 meters across, so about 3 times larger. That's about 20 feet across on its mirror. To give you a sense of scale, James Webb, this purple thing on the bottom is its solar shield to block out the sun's light, and that's the size of a tennis court. James Webb is so large that it actually had to fold in on itself, sort of like origami, to fit into the nose cone fairing of its rocket. But what really makes the telescope so very impressive is not only because the telescope is so large, it gets this extremely high precision, but James Webb Space Telescope also has access to wavelengths that Hubble hasn't. So right here, this is the wavelength range that Hubble can normally observe. And given that James Webb is about 3 times larger, and can observe actually about a factor of 2 more given its orbit, James Webb Space Telescope is roughly at least 2 to 3 times more powerful than the Hubble Space Telescope. So with Hubble, we're mostly focusing on water because that's the wavelengths that its telescope operates at. With the James Webb Space Telescope, we can look for other molecules such as carbon monoxide, carbon dioxide, sulfur dioxide, sodium, all these different molecules that we finally have access to with the launching of this new space-based telescope. So again, every single observation of James Webb is really changing the entire field every single day. This is why we're very excited, and I am very lucky to work on the Nancy Grace Roman Space Telescope. This is NASA's next astrophysics flagship mission that is launching no later than May of 2027, but perhaps as early as October of 2026. The scope is the same size as Hubble, again, 2.5 meters across, but thanks to its new design, it has 1 to 200 times the field of view of Hubble. So for every one Roman image, it would take Hubble 100 to 200 images to take. And also thanks to advances in technology, Roman can actually do Hubble quality science 1,000 times faster. And Roman will be a general survey instrument. We'll be using it to study infrared astrophysics, dark energy, cosmology, and exoplanets. And Roman will actually be an exoplanet discovery machine. It will be using the microlensing, the transit, and the direct imaging methods to observe transiting or to observe exoplanets. So Roman will actually be studying all the science behind all of those awesome Galaxy of Horrors posters that I showed at the beginning of my talk. It'll be doing exoplanet science. It'll also be investigating dark energy and dark matter, for example. The Roman Space Telescope is named after Nancy Grace Roman. She's NASA's first chief of astronomy. She was also NASA's first female executive. And she's sometimes called the mother of the Hubble Space Telescope because she was one of the major proponents who was fighting to get Hubble launched. Not everyone was convinced that investing in the Hubble Space Telescope was worth the time and the energy and the effort. And Dr. Roman was very successful in sort of getting the entire scientific community excited, getting Congress excited, who funded Hubble, and also the general public excited in their support of the Hubble Space Telescopes. We really have her to thank for Hubble and space-based observational astronomy. And in her honor, the Roman Space Telescope has been named after her. So here's an example image of what we expect to get from Roman versus Hubble. Right here, this is in a very iconic photo, the pillars of creation that were taken by Hubble in the early 90s. These are stellar nurseries where stars are being born right now. And in a single Roman image, we can get about 1 to 200 times the field of view of Hubble. So not only do we get the pillars of creation at Hubble sensitivity, at Hubble precision, but also we can get the entire context of the larger view as well. So Roman is very complementary to both Hubble and James Webb. James Webb is sort of like the zoom lens that gives us a lot of information about a localized part of the universe. Roman gives us that sort of panoramic fisheye view of the context of those observations. Roman also complements the Hubble Space Telescope as well. Hubble's still extremely useful and crucial because that's one of the very few instruments, if not the only instrument, that gives us access to the ultraviolet part of the sky. So we really still need Hubble around even after Roman launches, so they can work hand in hand to get us observations of the same object at different wavelengths, for example. As I mentioned, Roman will be a planet discovery machine. We'll be discovering tens, if not hundreds of thousands of planets using Roman, using the transit, the microlensing, and also the direct imaging methods as well. I've been working on myself the Roman chronograph for the last 5 or 6 years. And what the Roman chronograph will do is this will enable us to sort of take the next steps in direct imaging. Direct imaging has mostly been done on large ground-based telescopes, 5 meters or 200 inches or larger. And with those ground-based telescopes, we've mostly been able to really only observe really young planets that are still radiating a lot of their heat very far away from their host star. What the chronograph will enable us to do is to push that boundary in further, to looking at planets that are closer to their star, that are also older and therefore dimmer and cooler, more temperate. So we can actually start to observe using direct imaging true Jupiter analogs for the first time ever. And this is incredibly necessary because this will enable us to take the next step to next generation missions, such as the Habitable Worlds Observatory. This is NASA's next flagship mission that'll be launching in the 2030s or 2040s that is being explicitly designed right now to look at Earth-like planets around sun-like stars. But in order to get from where we are to where we want to be, we need the Roman Space Telescope and its chronograph to sort of give us that stepping stone so we can learn what instruments to use or not use, what methods to use, what sort of post-processing, data, software, mission design. And from all those lessons learned from Roman and the chronograph, will be feeding them in directly to those future missions as well. So you might be wondering why even bother with the ground, because space-based telescopes aren't limited by Earth absorption. We're minimally impacted by sunlight, you can observe by just simply by pointing away from the sun. However, these resources are extremely precious. We're limited both in available time and the wavelength space that we have. Again, the oversubscription rate on Hubble and on James Webb are about 10 to 1. There's a lot of folks that aren't getting their proposals accepted, for example. But this is why ground-based telescopes are still extremely important because there are, many more ground-based telescopes out there than space-based ones. And even a lot of them today, their price have come down that folks, amateur astronomers, are able to use relatively modest systems at relatively cheap prices to observe and help make impactful scientific observations in astronomy, much less exoplanets. So there is still a very crucial part for ground-based telescopes, amateur astronomers, folks such as yourselves, to help us to get more information, to help leverage and expand the science operations of these space-based telescopes as well. So now that's how we find a planet. That's how we can sort of figure out if it can support life or not. This brings us to our final step of finding life. So let's pretend that we launch a spacecraft out into the outer parts of our own solar system. And as that spacecraft is leaving the Earth, it might point back at the Earth and, sort of figure out through spectroscopy, what are the signals, what are the bumps and wiggles in the Earth that indicate that life exists? So we can look for evidence of oxygen that's produced by plants, for example, or we can look for water on its surface that we know that life requires to survive. We can also look for signs of biological activity like methane that's given off by cow farts, for example. We can take all these different molecules together and sort of infer that life exists on the surface of a planet. However, we have to rule out all other explanations. Water, for example, is one of the most common molecules in the entire universe. And we're actually finding water in almost every single exoplanet's atmosphere that we found to date, just simply because it's so common. We're finding methane, for example, in a lot of these exoplanet atmospheres. But a lot of these planets we think are inhospitable for life. The planets are gas giants, or they're really close to their host star, so they have temperatures that are not conducive to life. And this is one of the newest frontiers of exoplanet science. It's called astrobiology. So where astronomers are thinking up ways that life could form in hostile environments or alien environments. And also, what are those signals that we need to be looking for in order to conclusively determine that life survives on their surface? And that mixture of molecules, those bumps and wiggles that we need to look for, that's actually one of the biggest outstanding questions right now in the field in my mind, is what to look for and what sort of planets to look for. So that's why planetary science missions, such as the launch of Europa Clipper just about 2 weeks ago from Kennedy Space Center, that's why that's so exciting to me, is because that mission is going to be characterizing the oceans of that moon of Jupiter. And perhaps there might be life on the moon of Jupiter right now on that ocean moon. So if we find life out there in our own solar system, that greatly changes our view of the entire universe. We go from that sort of Earth-centric, human-centric bias of looking for those types of planets to really opening the doors to new possibilities, which is really exciting. Alternatively, we can also try to talk to aliens as well. Voyager 1 and 2, they were launched in the mid-70s. They did this grand tour of the solar system, and they had these golden records on board. They had recordings of pictures of the Earth, but also sounds and greetings from various cultures on the Earth as well. On the cover of the record, it taught aliens how to read off the record to get the signal from it, how to display that signal on your TV screen, and then exactly where that signals come from. Similarly, scientists in the mid 70s sent out a signal from Arecibo. This was once the world's largest radio telescope. It would fit in a valley on a bunch of different mountain ranges in Puerto Rico. And they sent out this message on the right to this globular cluster of stars in 13. And this message said, hey, aliens, we think we're smart. We know about counting. We know about molecules. We know about DNA. Here's what we look like. We're humans. Here's where the signal came from. Here's the sun. Mercury, Venus, Earth elevated because that's where the signal came from. Mars, Jupiter, Saturn, Uranus, Neptune. And folks, this was the mid 70s when they didn't know any better. They had Pluto on this map. And Pluto is not a planet, so this is absolutely wrong. And then here's a little side view of Arecibo itself. You can actually try to send messages to potentially aliens or civilizations as well. More contemporary, about 15 years ago, there were some messages sent to this extrasolar solar system called Gliese 581c. This system is interesting because these two planets, C and maybe also D, are within the habitable zone of their host star. So they did a competition on a social network called Bebo. Here it was big in Europe back in the day. They sent a message back then in 2008, and it will arrive in 2029. And if there are aliens there, if you're able to interpret the signal, the reply will be coming back in 2049. So get ready for some really awesome memes from back in 2008, maybe coming back in 2049. All right, so where are we now? So, despite what the History Channel and Ancient Aliens might be telling you, we have yet to make any conclusive detection of extraterrestrial life. And the question is, why haven't we? We now know today that there are at least as many planets as there are stars in the sky. And potentially, with so many planets, there should be life out there. It sort of stands to reason that there might be other alien life out there. Well, maybe our technology isn't good enough. It really wasn't until the discovery and the invention of a digital camera, I would argue, that we had the technology needed by the mid 90s to know how to look for exoplanets. Or maybe we just haven't found them yet. Maybe they've been talking to us from this part of the sky. We've been focused on this patch of sky. Jill Tarter, she's the SETI scientist who is the inspiration for the book and movie Contact. She had a really great analogy. If we took the entire universe and we shrunk it down into the size of the Earth's oceans, we really only explored the equivalent of one cup of water's worth. So while we think we know a lot about the universe, there's still a lot more out there to explore and discover and understand. Or maybe, most depressingly, maybe we aren't all alone. Maybe life is extremely rare and doesn't happen very often, and life only exists here on Earth. Personally, I think that alien life has to be out there, and I'm really excited that with the launching of the next generation space telescopes, hopefully in the 2030s, 2040s, that within my lifetime we'll be able to finally answer that question. But definitely don't be like my brother-in-law, Ryan Reed, who definitely thinks that I am hiding the fact that aliens exist. This is a real picture of my brother-in-law, and he always tries to convince me that to spill the beans that we've discovered alien life out there. We have not yet. I wish that were true, though. So, again, to wrap up, we've had this incredible foundation given to us by ground-based telescopes that are continuing to do impactful science. We are getting data from Hubble, from James Webb, from TESS. We're about to get data from the Roman Space Telescope launching in perhaps as soon as 2 years. But what's really exciting is by building upon this foundation of all these ground and space-based telescopes, we have launching in the 2030s or 2040s the Habitable Worlds Observatory. Again, this is a space telescope that is leveraging all these lessons learned from all these amazing space telescopes. And within our lifetime, this will finally answer the question, are we alone in the universe? So again, thank you again, everyone, for coming out tonight, and happy to take any questions you might have.
Great. So if anybody has any questions, I have the microphone here so that we can hear you guys better. I'm going to turn on the lights. You can see them as well. Anybody want to raise their hand? Over here, Astronomy Club, you want to say anything? Turn on the light. Hold on.
I'm the astronomy club president. My name is Safina, and I have a question about how you're planning to launch the Roman telescope, because I imagine it's going to be bigger than the Webb James. So, will it be harder since the Webb James have to fold into itself? How are they planning to get the Roman out of the planet and into outer space?
Yeah, so luckily Roman, its physical size actually fits within the nose cone fairing of the SpaceX Falcon 9 Heavy rocket, but Roman's a bit heavier than James Webb. So James Webb had to fold in on itself to sort of fit inside that. But since Roman is a little bit smaller in its volume, it doesn't have to do any interesting folding really. The only thing that really folds out is its high gain antenna and its solar arrays. Let me try to find a quick picture of Roman. One quick second so I can show you exactly what I'm talking about. Doop. All right, so right here is a picture of Roman. You can sort of see its high gain antenna that actually folds in and out, but also its solar panels flip out as well. So when this is being launched, this solar panel right here is actually folded in, so it's more flush against the outer barrel assembly, and this one as well. And then it's a deployable aperture cover, it's DAC, that's its sun shield that also folds out as well. So these three things are the only things that sort of move when we launch it. Actually, to design the DAC, the sun shield, they've actually talked with origami experts to learn how to best fold this and unfold it as well. So Roman otherwise, then the high gain antenna, the solar shields, and the sun shield, solar panels and the sun shield, those are really the only things that it needs to fold in and to fit on the top of the Falcon 9 Heavy. Yeah, great question. Thank you.
Well, I do have a question. So you were talking about the astronomers that wanted to publish. So they would analyze the data and basically give their own interpretations of what the data is, and that's what they publish. I was curious to know more about that.
Yeah, so that's all through Exoplanet Watch. And we have some students, for example, that are analyzing the timing of these transiting exoplanets to sort of figure out when the next, or better, more accurately predict when the next transit occur. So they can actually use their own data that they get from us, or they can actually go on our website and look at the observations that other users have contributed, whether that's from the micro observatory through us, or also we have amateur astronomers across the globe. So you can actually have collaborations. We actually have a high school student that's building his own collaboration right now to do his own study. So the easiest way to get involved in this is just to go to our website, Exoplanet Watch, and then from there, you can sign up for our newsletter. You can hop on our Slack channel and you can talk to lots of friendly people who run to any issues. And I'll actually get it to my own cell phone because I have Slack on my phone. So you can actually ask us questions on how to get involved as well. And we'd love to have any of you.
So is there, what is, I think you mentioned it, but again, what is the main difference between the Planet Hunter website versus the Exo Planet Watch?
Yeah, so Planet Hunters, what they're doing is they're looking at data taken by the TESS mission. So TESS is that full sky survey instrument, and TESS will stare at a portion of the sky of hundreds of stars, and it'll wait for a transit event to occur. And TESS has its own pipeline analyzing the data to sort of identify those potential candidate planets. But the pipeline isn't perfect. It will miss some events. And this is why we need humans in the loop still. This is one of the reasons we need humans in the loop for Exoplanet Watch as well. Is because humans are great at finding patterns and doing pattern matching. So you might actually find an exoplanet that the official pipeline coded up by professional astronomers might have missed. So what you can do is you can go on the Planet Hunters website, just search Planet Hunters TESS, TESS, and from there, you can actually, on your own computer, help analyze data and discover exoplanets. And I think there's actually been a handful of planets, about 10 or 15 or so, if I'm remembering correctly, that have actually been discovered by amateur astronomers across the globe. And then professional astronomers have then gone and confirmed those planets as well. And we actually hope to make something similar to Planet Hunter's test with the Roman Space Telescope when that launches, because that will have hundreds of thousands of planets that you can help us discover as well. Exoplanet Watch is a little different in the sense that we're trying to observe planets that have already been discovered. So we're trying to get follow-up observations, repeated observations of those previously discovered planets to help refine the times to then better schedule time on James Webb and Hubble to use them more efficiently.
Anybody else? I have tons of questions, but I don't want to hog the. Any astronomy club? Anything else? Will they learn how to like, because I was hearing the explanation, but if they go and they sign up, is there a tutorial there as well to sort of better know how much math and how much of astronomy do they have to know before they go on there? Or can they learn a bit more and then obviously practice it while using the softwares on both sides?
Yeah, yeah, we have both written tutorials and also YouTube recorded video tutorials as well. We also have bi-weekly meetings and a really helpful Slack channel. So if you have any questions or run into any issues, people across the world can help you basically 24/7. So if you do run into any issues, please let us know. Or alternatively, if you think we're missing something on our page or we can make something more user-friendly, let us know because we're always looking to improve things. We've actually gotten a lot of great input from our users on improving the project and have done a lot of great improvements from there, thanks to their input.
I guess, because again, I don't want to hog it, but I sort of, I guess I'm the one who's brave enough to ask the questions, I'm not sure, but my question actually is about AI. What is your prediction about how it's going to be used and whether it's going to eliminate the use of citizen astronomers? Is it going to be a tool for citizen astronomers? And what do you think it's going to facilitate?
Yeah, I guess what we've already seen for astronomy, at least, machine learning and AI have been used to help discover exoplanets, but these aren't perfect things. There's always needing some a human in the loop to make sure that things are operating correctly or that things don't fall through the cracks. And ultimately, at the end of the day, AI is programmed by humans, and humans, we make mistakes or we don't think about different things. So AI is not perfect. So hopefully there's still a job out there for me despite, for example, despite AI coming on the scene too. So there's still definitely a need and opportunities for humans to definitely be in there and literally leverage AI as a tool instead.
I'm the vice president of the astronomy club. We just wanted to ask what your role was on the Roman telescope.
Yeah. So my role on the Roman Space Telescope is I'm the deputy project scientist for communications. So I've always loved doing education and public outreach. So I get to really do that for the entire mission, which is a total blast. I'm also doing that for the Habitable Worlds Telescope as well. So just joined that mission about 2 months ago or so. So I've always loved giving talks and lectures and mentoring students, and I'm really excited to be able to do that with my new role at NASA Goddard. But what I also get to do when I'm not giving talks, for example, is I'm helping out with project work and formulation. So, for example, I'm working on how best to use our instruments by calibrating out sources of error. And then on Hab Worlds, hopefully I'll be part of the discussion as well on designing perhaps some of the wavelengths that we use, or the mirror sizes we use, or the observing techniques. So I've always been extremely interested in NASA and NASA missions. I was the little nerdy kid that had space shuttle wallpaper in their bedroom when I grew up as a little kid, and I've never grown out of it. Yeah, I can see you judging me there in the front row, but yeah, I had nerdy space wallpaper in my room, and I never grew out of it. I always want to be part of NASA missions. So I'm honestly super grateful that I get and honored and lucky that I get to be part of this mission and to do this. So.
Question?
Hello, so I was wondering, I know you said that the Hubble telescope is pretty old technology compared to the newer ones coming out, and I was wondering, how have you been able to update the software if you've been able to for the Hubble, or are you still using the old software that was programmed when it was manufactured?
Yeah, so Hubble is really great in that way, in that it's in low Earth orbit. So Hubble can be serviced by human spaceflight. And Hubble was originally launched in 1989, and there was actually an issue with one of the Hubble's mirrors on board. And it wasn't until 1992 when they launched and replaced one of the instruments on board that they were able to correct for Hubble's sort of give Hubble glasses in a sense by correcting for its vision. And then over time, as instruments failed, because maybe just over time, just like your old iPhone might get old and bad, or your car might break down, there's only so much things you can do to fix things. So they actually traded in and out and replaced instruments on board of Hubble. And they've actually upgraded some of the system software as well. The last upgrade of the software that runs on board of Hubble, I think, happened in the early 2000s, if I remember correctly. But people are always inventing new techniques to analyze the data. So for exoplanets, for example, or any part of astronomy, when a new method comes onto the field, like machine learning or AI, people will leverage that new software to better interpret old data. So there might be a discovery lurking in some data taken in the mid 90s. And what an astronomer will do is they'll go back and reanalyze that data with a new data analysis method such as machine learning or AI, and they'll actually discover something new in an old data set. That's a really cool question. Thank you very much.
Yeah, that's from engineering, one of the engineering students. We have that kind of here. Anybody else over here? Yeah.
I'm like the astronomy club secretary, and I wanted to ask if there's ever going to be a day where we can get close enough to those solar systems where if there's gonna be like if we can get close enough to them to like genuinely like observe them, yeah.
Yeah. That's a really great question. So the nearest solar system to us, the nearest exoplanet to us is likely in Proxima Centauri, and that's what, three something light years away. So it takes at the very least any signal that we send out or receive from Prox. Um, 3 years to get one direction. So, but if you wanted to have a conversation, that would be taking at least 6 years. We'd have to send out a signal to them. They'd have to immediately reply and send a signal back to us. So it just really truly shows how vast space is, right? But if we really wanted to visit there, it would take, I think the latest I saw was about 10,000 years with current technology. So we would have to do some sort of multi-generational mission out there where you'd have to like either cryogenically freeze people or have multiple generations on a one-way trip out to there. And that's something that really needs maybe something more sci-fi to be solved, like light speed travel or warp drives or something like that to span space. There is some science fact in it, actually. If you haven't seen the movie Contact, I definitely recommend it. It's actually a really great science fiction movie. It was written by Carl Sagan, who is the Neil deGrasse Tyson back in the day. And they actually were able to discover a form of warp drive effectively by Carl Sagan actually going to one of his friends, a cosmologist, and saying, "Hey, I have to get my character across the universe really quickly, but I don't know of a way to do this because space is so vast." So what they did is they crunched numbers and they found out that wormholes can actually be used to help transport folks across the universe. Problem is that wormholes are at the center of black holes, and surviving the pull of a black hole is kind of dicey at best. Perhaps really smart people in the future will figure out how to survive that trip and we can leverage wormholes for travel. Until then, we're kind of stuck on more conventional methods and we're not going to be a proxen anytime soon at all. Great question. Thank you.
Contact is actually my favorite book and movie of all time. So
Yeah, they're both great. Definitely recommend reading and watching it for sure.
that answers why the journalism TV film teacher is doing the NASA experience. So, anybody else want to ask questions? Engineering students, we got a couple back here. You wanna, yeah, okay.
I have a question about your personal opinion, but beforehand, I did want to mention that my vice president has a really sizable poster of the space shuttle on her wall.
Nice.
My question was, what's your opinion on media involvement when it comes to like sci-fi movies? Do you believe that they are a positive impact most of the time? Or do you believe that sometimes it brings down a little bit of like the space involvement?
Yeah, definitely some astronomers feel very differently. Some are extremely opinionated and they like to call out every single scientific inaccuracy in these movies. Personally, I see them for what they are, really great entertainment. Like I said before, I love Star Wars so much. I almost love Jar Jar Binks. That's how much I love Star Wars. So that tells you how much I love it. And honestly, I take it for entertainment. And if it gets other kids interested in astronomy or science or space or NASA, then that's great. Um, I know that when a TIE fighter explodes in space, it doesn't really make that noise, or if it passes by you, it doesn't really make that noise. But it sounds so damn cool, you know, and it just really helps to add to the entertainment. So if you can take it with a grain of salt, in the sense that, knowing that some of these things are beyond us or not necessarily scientifically accurate, it still provides really amazing entertainment that can also inspire people to be excited and support space. And at the end of the day, that's what we're all really looking for.
Anybody else? One of the things that actually I would like to learn, but I don't know, we have about a few minutes left, and I can probably just ask you, ask you guys later, because it has to do with my own personal work of masters and stuff. But what has, I don't know, I haven't read up on this, but has is this sort of change that happened a couple of years ago? Because I know that when Contact came out, the whole, search for extraterrestrial life was still sort of at that point. I know that the real life character had the real life inspiration for that character had gotten some fire from having chosen that particular career. It wasn't as highly accepted. But when did the change occur? And is it because obviously eventually we do have to get off the planet because of the solar, even though it's thousands of years in the future, is there like a directive that NASA sort of decided, yes, this is definitely what we need to do because it's going to be the survival of our species? Or do you want to talk about that? At least, I don't know if anybody else is interested, but I'm very interested in this question.
So focusing on the depth of humanity. Perfect. Great thing to end on, folks. This is really nice. Wow. As far as I'm aware of, there's no directive by NASA for future plans. The Earth will not be around forever. The Earth is about 4.5 billion years old. It will last only for another 4.5 billion years before the sun expands and engulfs the Earth. So there is a sort of time limit on how long the Earth can last, regardless, not taking into account things like global warming or climate change. Um, there are people that are thinking about, colonizing space, and that's actually one of the sort of more popular tropes in science fiction is discovery, and looking at the human race. Discovery has always been a part of what we are as a species, and exploration and understanding out there. So naturally it seems like, well, we have folks traveling across the world in giant ships. We could also have out into space as well. Unfortunately, I think our generation is born too early for that, as amazing as that could be. Um, but it's probably, if I were to put money in, hopefully before we kill ourselves, we can do space travel and exploration as well. But in so much as an actual formal declaration or sort of mandate by NASA, I'm not aware of any.
Question. How do you believe space pollution will affect like future sightings or like astronomical discoveries?
I missed the first half. Would you just repeat that one more time, please? Sorry.
How do you believe that How do you believe that like space garbage, like old like mission? Yeah, covered footprint. Yeah, how do you believe that the old like remains from satellites is affecting the current discoveries or will affect the future discoveries from?
Oh, yeah, that's a really great question. If you look at maps right now, you can actually look at some computer generated images that sort of shows the derelict satellites that are up in Earth's orbit. And sometimes there's like thousands, if not hundreds of thousands of satellites already up there, or even just bits of satellites up there in space that are, that are limiting what we can actually launch in space. So, for example, there are some orbits up there that are very highly prized, and nations will sort of vie, and companies will vie against each other to get access to those very important geostationary satellite orbits, for example. Um, and right now, we're actually seeing an impact on astronomy. So, for example, there are some communication satellites that can show up in some long exposure images as well. So, it can actually have a negative impact on astronomy. So, perhaps there might be missions in the future that can help clean up the space junk and remove some of those satellites out there so we can launch more things or get more access to the skies. Hopefully, hopefully we'll still have access to some nice skies out there and be able to tackle this directly.